So this work with Eric Lander that was mentioned in the introduction was a paper we wrote about how the genome would be covered if these reads were located randomly according to the Poisson process down the genome. And the key parameter was how much overlap you needed between two reads to say, I believe they're together. And we had a bunch of formulas that people used in sequencing projects. And in fact, Illumina recommends to people in their current distribution that they use my work with Eric Lander. Paired end reads, where you get two reads where you know approximately how far apart they are, is used in almost all these projects, and that makes the statistical analysis much more difficult. A guy from Berkeley has a nice information theory analysis of coverage, not useful to practitioners, but a nice paper. But our formulas really aren't applicable anymore in these days of huge deep coverage. And wonderfully, a colleague of mine at USC has a completely different approach where he's bringing some statistical ideas to bear on this. So let me try to tangle you up in some more biology here. We have molecule 1 and molecule 2. They both get amplified, but in fact, your selection, you may have a whole bunch of the molecule 1s and almost none of molecule 2 that maps to this place. I'm trying to say that the libraries that people are doing the sequencing from are highly non-uniform, or can be highly non-uniform. And the word complexity is used. This is high complexity where it's all these guys have uniform frequencies. Lower complexity where some are, got away from me there, where some are amplified much more than others. So his scheme allows you to take, here's 3 different libraries, and these are fraction of unique reads in each of these libraries. So after 1 million reads, this one has a high percentage of unique reads. This one has a little over 97%. This has about 98%. And yet, if you were to do 50 million reads, the blue library, if you had to choose between the blue and the red, the blue library is much better. How could you tell that? It looks like you're going much better there. And his approach goes back to, I think, Fisher and I.J. Good, back to something called capture-recapture. I don't know if you know this story, if you're trying to count butterflies here. If you're trying to count butterflies, you catch a bunch of butterflies, you paint them all a color, you turn them loose, you come back the next week and see what fraction are new as composed. That gives you, cool. Brad Efron in recent times advanced this by studying how many words did Shakespeare know if your evidence is the plays he wrote. How many additional words did he know and didn't write down? How can you test that? The way this works is you do word counts of his plays. How many words did he use once? How many words did he use twice? How many words did he use 100 times? ... And your question you're really trying to answer, how many words did he not use at all but he knew? And that's the same in the genome. How many bases are left out there to learn? And this is just wonderful work of Andrews, because the size of the data he's working with dwarf anything Efron or anybody else was doing, and those methods numerically and statistically don't work anymore. So this is pretty cool work.